The history of holography dates back to 1948, when Dennis Garber invented it to enhance the image resolution of electron microscopes. Optical holography, which emerged in the 1960s, involves using laser light to reconstruct a three-dimensional image of a physical object. Transmission holograms require laser light of a specific wavelength, similar to the one used in the creation of the hologram. This experiment focused on capturing a transmission hologram. In this experiment, we constructed an optical setup to capture a transmission hologram, which involves recording a three-dimensional image using laser light. The experiment focused on evaluating the effect of incorporating a spatial filter to improve the quality of the laser beam. The spatial filter helped enhance the beam profile, which was crucial for achieving a clear and accurate hologram. After improving the setup, we used holographic film and a developer to create a hologram that could be viewed under a red laser beam. The history of holography dates back to 1948.
One of the aims of our experiment was to establish a more Gaussian beam profile. A Gaussian intensity distribution is modeled in the first equation, with I naught being the intensity at the center of the beam, x minus x naught being the displacement from the center of the beam in the x direction, and w naught being the beam waist. Correcting the profile of the beam should result in the beam becoming less diffused by the time it reaches the end of its path, and therefore would give us a sharper image. A spatial filter consisting of an objective converging lens, a small pinhole, and another collimating converging lens should help us with this goal. The ideal diameter of the pinhole for the spatial filter is given by the second equation, where W naught is the beam waist again, lambda is the wavelength of the laser light, and f is the focal length of the objective lens.
Our experiment setup began with setting up a spatial filter, constructed using a laser with a 633 nanometer wavelength, an objective lens with a 300 millimeter focal length, and a pinhole with an ideal diameter of 0.2 millimeters, positioned at the focal length of the object. Following the spatial filter, a converging lens with a 175 millimeter focal length was placed at an equal distance to collimate the beam. A variable beam splitter was calibrated using photodiodes to achieve a 53 to 47 intensity ratio between the object and reference beams. Mirrors directed both beams to diverging lenses with focal lengths of negative 25.4 millimeters, expanding the beams before reaching the holographic plate. The setup included alignment with a white card for precise placement and exposure. Finally, a shiny white rabbit figurine served as the object for the hologram, positioned in the path of the object beam near the holographic plate. This is a diagram of what our setup looked like. As you can see, the laser initially goes through the spatial filter across a 121-inch range and then encounters the beam splitter, which splits the beam 82 inches straight through and 82 inches down. This is where the mirrors come in, which direct the beams to the object. The one to the right being the reference beam and the one down being the object beam, which directly hits our object. Both of these beams, before encountering the object, go through a beam expander to enhance the laser and exaggerate the reflection/shadow of the two interfering beams when they hit each other around the object. Below the diagram is our object. We named him Simon. And underneath Simon are the names and focal lengths of the lens we used for converging various beams.
To evaluate the effectiveness of the spatial filter, we took photos of the recombined beam projected onto a blank screen where we would eventually place the holographic film, both with and without the spatial filter included. We ran these photos through Python and had it estimate the beam intensity across the x direction by counting the number of illuminated pixels per column of pixels. We isolated the same central part of the beam to analyze for each case. We then fit both of the generated datasets to the Gaussian distribution equation, leaving the peak intensity and beam waste as open parameters, and we then compared the two fits. The corrected beam profile had a reduced chi-squared value of 2.62, compared to 3.12 without the spatial filter. The mean and standard deviation of the residuals from the two fits were very similar, but a lower chi-squared indicates that the corrected beam profile conforms more closely to a Gaussian fit. This also means the corrected beam will likely be better to use for capturing a hologram.
The projected hologram was captured with a 633 nanometer laser, passing through and reconstructing the interference pattern as a visible 3D image on the planar surface used for projection. The projection displays a silhouette of our rabbit figurine. The bright laser glow indicates the laser's coherence and alignment, and the interface fringes and the diffraction artifacts that are visible around the edges, which is characteristic of a holographic reconstruction. This next slide is showing the interference pattern and the silhouette of the rabbit. The projected hologram was To sum up, we successfully implemented a spatial filter and a transmission hologram with an optical setup, which significantly improved the beam profile by reducing the diffusion in the beam, which subsequently allowed us to capture a crisper hologram image on the holographic plate. One major setback, however, that could have affected the results is the exposure time for the holographic plate. Although we use a conservative 15-second exposure within the recommended 10-second to 40-second range to avoid overexposure, a slightly longer duration may have improved the hologram quality, and for next time, if there ever is a next time, we would change that. Additionally, the relative positioning of the object and the film was very difficult, as the final holographic image does differ slightly from what's visible on the plate in the same position. But to conclude, we felt very satisfied with our project and with our results.